Okay, we've hinted around about the normal force. We've basically done the normal force, but here we'll actually define it and give you some more insight to it. Define the normal force. Normal forces are perpendicular to the surface of contact. That's why we use the word normal. Normal in physics doesn't mean normal versus abnormal. Normal means perpendicular. And some of you may have seen that word used to mean perpendicular in your math courses as well. Normal forces are perpendicular to the surface of contact and prevent objects from moving through each other. So if we have a concrete block here and it has a weight W, then what this normal force does, what its job in life, is to prevent this concrete block from falling through the table, from moving through the table. It exerts an upward force holding it up. So this is the normal force. Perpendicular to the surface. So if you have something that's sitting on an inclined plane like that, then the normal force would be perpendicular to this inclined plane. And going back to our cell phone example, remember the cell phone that was sitting on the table? Then that has a little bit more meaning now. There are two forces acting on the cell phone: gravity, its weight, and the normal force, just the same as this concrete block example here. And Newton's third law says that if the Earth exerts a gravitational force pulling that cell phone down, then that cell phone exerts an equal and opposite gravitational force pulling the Earth up. But it also applies, Newton's third law also applies to normal forces. If the table exerts an upward normal force on the cell phone, which prevents the cell phone from falling through the table, then the cell phone exerts a downward normal force on the table. Equal magnitude, opposite direction. That's the way that works. What holds the performer up? So we got a performer on the bottom here, and then another performer where their heads are making contact, or at least through some kind of a pad. What's holding this upper performer up? And you might say, well, it's probably a normal force of the lower performer's head holding the upper performer up and preventing her from falling to the center of the Earth. Let's do an example. A wood or a block. Here's your hand. You're pushing down on the block, vertically downward. And the question is to find the normal force preventing this block from falling through the, let's just call this a table. Well, and you're given the weight of the block. Let's apply Newton's second law. We're going to choose a coordinate system. We only need y in this case. We don't really need x. And look at the forces in the y direction. The net force in the y direction. Well, what are the forces in the y direction? Well, there's this normal force which points in the same direction as y. Because of that, its component is going to be positive. Then there's an 11 Newton force pointing down opposite the direction of y. So we put it in with a minus sign. And then a 15 Newton weight of the block. It exerts a force on the block as well. and pulls it down toward the earth, which is opposite the y direction. What matters here is not up or down, but whether it's opposite to or parallel to the axis that you're looking at. We're looking at the y-axis. It's up. The gravitational force is down. Therefore, the y component of the gravitational force is negative. So that's why this is negative. And then we're setting this all equal to 0. Why is that? Well, the acceleration of this block is 0. It's just sitting there. So we just get to put in an acceleration of 0. We're following the phases steps here, but in a fairly rapid fashion. 11 plus 15 is 26. They're both with minus signs, so you bring them over to the right side, and you get a 26 Newton normal force of the table. This is the force of the table on the block. All right, fair enough. Well, let's do another case here. Instead of pushing down with your hand on this block, let's hold up this block with a rope, but not hold it enough, not pull up on it hard enough to cause it to lose contact. So now we've got an 11 Newton force that's up, but everything else is the same as it was. So instead of the 11 Newton force being down, it's up in the plus y direction, minus 15. So we got 11 minus 15, that's minus 4. Bring it over to the right side, and we get a normal force of 4 newtons. Why is this force less than the case A here? Well, because you've lessened the force of contact, that normal force of contact between the block and the table, by lifting up on the block instead of pushing down, pushing it harder into the table. Define apparent weight. The apparent weight of an object is the normal force acting on that object, which equals the reading on a scale. So this is a definition of apparent weight. It is nothing more or less than the normal force acting on that object. And it's the normal force that you read on a scale. So when you stand on your bathroom scales to find your weight, what you're really reading on that scale is the force of the normal force of contact between your feet and the scale. You're not really reading the force of gravity. You're measuring a normal force. That's called your apparent weight. And you say, well, hold on, why are you making this distinction? Because it's just going to give me my regular weight, isn't it? I say, not so fast. Let's say you put your scale on an elevator, and the elevator's not moving. Well, let's say that the elevator is moving at constant speed. The velocity is constant or 0. Either way, it works fine. In either case, either for 0 velocity or a constant velocity, just moving with a constant speed between floors, not slowing up or speeding up or slowing down, then there won't be any acceleration. And in that case, you remember we worked out my weight to be about 700 newtons. Then the weight that you're going to read on the scale is going to be equal to your normal weight. However, if you're accelerating upward, then let's say you get on the elevator and the elevator is stopped at that moment, the door is closed, you push the button to the 10th floor, and during that short period of time while the elevator is accelerating, you feel yourself pressed into the floor. And then once it's moving at a constant speed, you say, whew, I don't feel that, I don't feel like I'm being pressed into the floor anymore. It's just moving along as if it weren't even moving at all. But during that short period of time while it's accelerating upward, you would read a greater force on that scale, a greater normal force on your bathroom scale, 1,000 newtons instead of 700 newtons. Similar for downward acceleration and free fall. So I'm going to actually do the calculation here to show what's happening. What are the forces on you when you're standing on the scale? And let's allow for the possibility that you're accelerating either upward or downward. We're going to apply faces. We're going to draw the forces acting on you, choose a coordinate system, write down Newton's second law to find the equations of motion. Ask which of these forces act in the plus y and which act in the minus y direction. Well, y is this way. The normal force of the floor on you is this way. So the normal force will come in as a positive because it's pointing in the plus y direction. What about your weight? Well, your weight is in the minus, here's plus y, here's the minus y direction. The weight is in the minus y direction, so it comes in with a minus sign. And that's equal to your mass times your acceleration. Now, this is the component of your acceleration in the y direction. So the apparent weight is this number right here, F sub n. It's just the normal force. Your true weight is W, whatever that is, 700 newtons in my case, equals the mass times acceleration in the y direction. So now let's go back to this diagram and ask, what this equation can help us see how we can understand. If the acceleration is 0, in this case, then that means ay equals 0, because a is the acceleration. So if we set the acceleration to 0, then the normal force is going to equal the weight. And so in that particular case, either you're stationary, you're standing on your bathroom scales, or you're moving on an elevator at a constant velocity, your reading on the scale will give your true weight. What if you're accelerating upward? Well, in this case, the acceleration is upward in the y direction. So is the component of this vector, A, is the y component of this vector positive or negative? And you'd say, well, I know that. The acceleration is pointing in the y direction. Therefore, its y component will be positive. So a positive acceleration in the y direction. If this is greater than 0 now, then that says you're going to add something to the weight and that the normal force will be greater than the weight. So that this says that the normal force is greater than the weight, or your apparent weight, aka your reading on the scale, will be greater than your actual weight. And you can go do this experiment, although I'm sure you can appreciate what will happen. You put the scales on the elevator, you step on the scales, you push the 10th floor button, and while it's accelerating, you're pressed down into the scales, and the scales are going to give a higher reading and a higher apparent weight. All right, a couple more cases. Suppose you're accelerating downward now. How can that happen on an elevator? Well, you make it all the way to the 10th floor. You stop, and you push the first floor button. You're stopped initially, and then the elevator starts moving down, starts accelerating downward. In that case, the acceleration is downward. And in that case, you feel this kind of light feeling, a little bit of weightless type of feeling. And in that case, you would expect that your reading on the scale would be less. Your apparent weight would be less than your actual weight. And sure enough, that's true. In this case, your acceleration is downward. That acceleration is in the minus y direction. The component of that yellow acceleration vector is going in the y direction is going to be negative. So ay will be negative. That means that when you take your weight, you're going to have to subtract something. This is a negative number. Subtract something from your weight to get your apparent weight, or the normal force. So this normal force will be less than your weight, and you read something on the scale that's less than your actual weight. If you're in free fall, if you suffer the unfortunate situation where the cable to the elevator snaps and you are in free fall, first of all, I feel for you. I'm sorry for you. But in the meantime, what's your apparent weight going to be? The answer is 0. How so? Well, your acceleration now, the component of the acceleration in the y direction, just like a lot of the problems we did in chapter 2 and 3, the y component of acceleration is a negative 9.8 meters per second squared. So that'll be minus g. So you'll end up with the weight, which is m times g, like we talked about, plus the mass times acceleration, but the acceleration in the y direction is minus g. Well, that's just mg minus mg, and that gives 0. So your apparent weight on the scale is 0. So while you're preparing to meet your maker, you will have 0 apparent weight. Great way to lose weight, but not recommended. A man stands on a spring scale in a moving elevator and notices that the scale reading is 20% larger than when he weighs himself in his bathroom. Which of the following statements is false? The elevator could be moving upward at constant speed. That's not possible because the acceleration is 0. And in this case, if it's moving at constant speed, there's no acceleration. The apparent weight equals the actual weight, W. The elevator could be moving upward with increasing speed. Well, that would mean that the acceleration is upward, and that would produce, like we talked about before, a scale reading that's larger. So that's true. The elevator could be moving downward with a decreasing speed. Well, what about that? So the elevator is moving downward with decreasing speed. So this would be the case that you go up to the 10th floor, then you push the first floor button. The elevator doors close. The elevator accelerates downward. You're moving at a constant speed down to the first floor. And then, just before arriving at the first floor, the elevator is decreasing its speed. It's slowing down as it approaches the first floor. That would be the situation. It's moving downward with a decreasing speed. Well, in that case, as you're moving downward and you're getting slower and slower as you're approaching that first floor, then the acceleration is in fact upward. And during that period of time, while you're slowing down, you'll see a higher reading on the scale. So this is also a possibility. This is true. You can get that. So we're actually looking at whichever one is false. Sorry, I shouldn't have circled these answers. This one is the false one. Either one of these could be the particular case.